This is our presentation on morph detection enhanced by a structured group sparsity. The contents of our presentation are as follows. First, we introduce the problem. Second, morphed image detection is discussed. After that, methodology, experiments, and results are explained. Detection of morphed images is of great significance in high-throughput border control applications. A morphed image in the middle is generated using genuine face images from two different individuals. Since the resulting morphed image inherits the characteristics of both subjects, it can be verified against both real subjects. Morphed images are usually generated using two approaches. In the first approach, known as landmark-based morphing method, two real face images are alpha blended in order to create a morphed image. To eliminate the ghosting effects in the morphed image, the average of the landmarks in both real images is used as the resulting landmark of the morphed image. In the second technique of the facial image morphing, a generative model, which is a generative adversarial network, is trained to synthesize morphed images. For detection of morphed images, some of the previous research efforts adopted handcrafted features such as BSIF, SURF, SIFT, or LBPH to detect morphed images. In this work, we employ group sparsity as a feature selection scheme to improve the performance of the deep morph detector. We first convert RGB images into the wavelet domain, and the group sparsity constraint is added to the loss function of our deep neural network, which implicitly picks the most discriminative wavelet subbands. As mentioned, all the input images are converted into wavelet subbands. So since the morphing artifacts lie in the high frequency spectrum, we do not consider the low subband in the first level of decomposition to be decomposed further. Instead, we decompose low-high, high-low, and high-high subbands in the first level of decomposition. And after 3 levels of decomposition, we get 48 subbands for each image. In this study, we use 3 datasets, VZAP17, LMA, and Morgan, and we do subband selection based on all 3 datasets combined, which is called universal dataset. We train a deep neural network with the training portion of the universal dataset, and in this deep neural network, the loss function includes a group sparsity constraint on the weights of the first convolutional layer, which implicitly selects the most discriminative wavelet subbands. We evaluate the performance of the trained deep neural network on the validation set of the universal data set, which leads to selecting the most optimal value for the group sparsity coefficient. So since the wavelet subbands are input of our deep neural network, our group sparsity constraint in the loss function of our deep neural network is actually a constraint on the weights of the first convolutional layer. After training our deep neural network, 20 most discriminative wavelet subbands are selected as shown in this picture. And as I mentioned before, this subband selection is done based on the universal data set. However, we use these 20 discriminative subbands to train separate deep neural networks for each data set, and we evaluate performance of the trained deep neural networks for each data set. In this equation, you see our regularized loss function of our deep neural network, which includes the classification loss, which is the binary cross-entropy loss, and the group sparsity constraint on the weights of the first convolutional layer. Lambda represents the group sparsity coefficient, and C represent the number of channels, N is the number of filters, H and V represent the heights, the dimension of the kernel in each channel. So based on this figure, the lambda equal to 0.003 represents the highest performance when our trained deep neural network is evaluated on the validation set of the universal data set. So the red curves is the optimal value for our hyperparameter lambda. In this figure, you see a summarized our methodology is summarized in this figure, which shows that 48 wavelet subbands are fed into a deep neural network, which has a constraint, group sparsity constraint on the weights of the first convolutional layer. After that, after training the deep neural network, 20 most discriminative wavelet subbands are selected, and then a morph detector is trained for each different data set. So the data sets in this study are VZAP17, Morgan, and LMA, and our deep neural network is Inception ResNet V1, and the size of our universal data set is as follows. In the training set of the universal data set, there are 1,631 bona fide and 1,183 morphed samples. The validation set of the universal data set consists of 462 bona fide and 167 morphed subjects. The test set of the universal dataset includes 1,631 bona fide and 1,183 morphed images. So in this slide, you see the DET curves when our morph detector is trained on the universal dataset in the left figure. And in the right figure, the DET curves when our morph detector is trained on each data set separately. Based on the right figure, our morph detector shows a very good performance on the VZAP17 and Morgan dataset, which means that most of the morphed images in these two datasets are detected. Also, the results of our morph detection is summarized in these two tables. The left table shows the performance of our morph detector when it is trained on the universal dataset. And in the right table, the performance of our morph detector when it is trained on the individual, trained and evaluated on the individual datasets. As you can see, for the VZAP17 and the Morgan, the results are very good. To show the functionality of our deep morph detector, we adopted GradCam visualization to see which regions are focused by our morph detector to label an input image as bona fide or morphed. In the left column, you see the GradCam visualization for the bona fide images, and in the right column, you see the GradCam visualization for the morphed images. Finally, we employed TSNE visualization to prove the functionality of the subband selection. In the left figure, a subset of the Morgan dataset is visualized for both bona fide and morph classes using TSNE. The same subset of the dataset is visualized in the right figure, but in the right figure, subband selection is performed on the dataset. As you can see, the in the right figure, the data points have become more separable compared to the left figure, which proves that our subband selection improves the morph detection, improves the performance of our deep morph detector. Thank you very much for your attention.